It also lives long enough that you can manipulate the particle in accelerators, and that you can measure properties of the particle with computers, which of course are much faster compared to the microsecond timescale. It's a spin half particle, and it encodes information about its spin in its decay. So like particles with spin, the muon's magnetic moment is related to its spin through these physical constants, some that are known externally, and of course the G factor. And this G factor is really the G that we talk about in G-2. Now, what happens when you put a muon in a magnetic field is that it will precess around that magnetic field, much the same way that a gyroscope will precess around a gravitational field. And if for a moment we imagined a universe where the only two things in the universe were the magnetic field and the muon, then we would predict that the G factor should be equal to 2. Of course, we know from QED, QCD, and the crazy virtual nature of our vacuum that particles pop in and out of existence all the time. And when these particles pop in and out of existence, they actually affect the rate at which the muon spin precesses in these fields. Now, we can do this for the particles that we know about. And the big question is, are there other particles that are popping in and out of existence that are causing the muon to precess in a different manner in a magnetic field? So I'll briefly highlight the status of the muon's magnetic moment before the Fermilab experiment. So our theorists can do an amazingly good job at taking the particles that we know about, processing them through the G-2 meat grinder calculation machine, and spitting out a prediction for what the muon's anomalous magnetic moment should be, what G-2 should be. And on the right-hand side, you can see the evolution of this calculation all the way up to this paper that was published last year that sort of summarized the state of the art of the theory calculation. Of course, the experiment itself is a bit agnostic. It doesn't just know about the particles that have already been discovered. It's also potentially sensitive to new particles. And the question is, are we able to process those through the machine and get a different number? And so about 15 years ago, the Brookhaven experiment made a measurement that had a tantalizing 3.7 standard deviation discrepancy from the current theoretical value. And so it was well motivated to try to improve on this and see if this is actually real new physics that is separating the theory from the experiment. And therefore, we designed an experiment at Fermilab in order to improve the precision by a factor of 4 and really definitively see if this is a mistake in experiment, a mistake in theory, or real evidence of a discrepancy between the two. And so I will leave the discussion of the standard model calculation beyond the standard model physics and possible interpretations to Dominik's talk, and really now jump into the experimental description. So I want to start by saying you take this muon and you put it in a magnetic field, and what the experiment really needs to do is this, okay? A precision measurement of the muon's anomalous spin precession frequency in a well-measured magnetic field will tell us how muons see the universe. So from an experimental point of view, if we want to get to this anomalous magnetic moment, G-2, what we're really responsible for is understanding how muons spin in a magnetic field and the strength of that magnetic field. The reality is, of course, a lot more complicated. So what are the main steps that we need to do to get a mu? Well, the first thing is that we have to build a racetrack for the muons. This is the ring that is at Fermilab with some people inside for scale. We need to inject and store polarized muons in that ring. We need to measure the decay electrons from those muons to determine the muon's properties. And we need to map and track the magnetic field over space and time. So I'll step through and give you some of the details on how we do this. So in terms of building the racetrack, we didn't start from scratch. We used the enormously successful superconducting coils that were built for the muon G-2 at Brookhaven. And we took apart all the steel and we transferred these coils very carefully onto a barge and eventually traveled 5,000 kilometers around the coast of the US up the river system until we got off the road right here near Chicago. At that point, we put the ring onto this trailer and brought it to Fermilab, where the community was extremely interested to see what we were starting here, what this magnet was all about. So it was really an excellent event to get people's interests stirred up and their appetites whetted. Then we basically installed the ring into the experimental hall that was built specifically for this on top of all the steel and began the process of reassembling the magnet. At the same time, the accelerator complex was retooling from the days of collider physics. And so we reused a lot of the campus and reconfigured it. The experiment works by taking 8 GeV protons and storing them in this recycler ring. We use RF to actually separate that pulse into several bunches. The intensity as a function of time sort of looks like this. And so you can see that with a sort of very narrow width, we have a highly intense proton beam. We then create pions by taking that proton beam and hitting a target made out of metal. And so we're able to construct a pion beam. And now the really important key here is that in the next step, we transfer those pions and let them decay, and we create a polarized muon beam, right? So we're interested in the spin properties, so we get the muons to come out in a polarized manner from the weak pion decay, and we allow them to then circulate in this delivery ring. So the muons will get ahead of the pions and the protons, which have a heavier mass. We're able to eject those out and then bring the muons into our experiment. We have that ring in a hall right there, and we store about 5,000 muons per pulse. Now, the way that the experiment is structured is that the entire measurement takes place in 1,000th of a second. Okay, and we repeat this 16 times basically every second, and then we repeat it over and over again for months and years. So I find it fascinating that all of the physics that we care about is generally taking place just in this blink of an eye, and our job is to keep things stable and repeat it over and over again. Okay, so there's 2 really important objects that are necessary for us to keep these muons in the ring. The first is a kicker. So when we inject the muons up this beam line through the outer steel of the magnet through a hole in the magnet, we come in at a radius that is not the optimal storage radius. And what we need to do is we need to transfer the muons onto the appropriate orbit. So on the very first turn, we create a very fast pulse, a fast magnetic pulse using these plates right here in order to impart a little bit of momentum in the outward direction to move the muons from this blue orbit to this sort of central orbit that we care about. At the same time, if the muons have any vertical component to their momentum, they will quickly spiral out of the ring, and therefore we use electric quadrupoles to provide a vertical restoring force and keep the muons in the center of the ring. Now, one consequence of this is that as the muons travel, they'll undergo oscillations in their vertical and in fact in their horizontal motions. And so this is really important detail for the experiment. The reason I'm showing you these 2 things is because both systems operated in a non-optimal manner in the first run of the experiment, and basically we needed to analyze some of their effects on our result, and I'll tell you a little bit more about those. Now, what happens to the muon spin when we've injected this polarized beam? Well, the first thing that happens when we look at the vectors is we can consider the momentum. The momentum of the particles travels around this ring, and it has a frequency that corresponds to a cyclotron frequency, which is proportional to b. But if you look at the spin vector, it has a term that looks just like the momentum vector, plus an additional term which is proportional to g minus 2. And what this means is that this blue vector, the spin vector, starts to advance with respect to the momentum vector. And if we take the difference between those two, or the beat frequency between those 2 vectors, we construct this anomalous spin precession vector, how much the spin gets ahead. And we see that it's proportional both to the strength of the magnetic field and the strength of the anomalous magnetic moment. So when we make a measurement of how fast muons spin precess in this field, it's very important that we understand the field. Otherwise, we might attribute a faster precession rate to the anomalous magnetic moment. So we have to actually measure both very, very well. Another really cool feature is that this frequency is proportional to the difference of g from 2, which is why the experiment gets its name. It's not proportional to g directly, but it's the part of all these contributions to g that make it greater than 2 that the muons precess with this extra frequency. Okay, the third step is to measure decay electrons to determine the muon's properties. Every 15 degrees around the ring on the inside radius, we have these calorimeters. They're made up of lead fluoride crystals, which you can see in this image here. They're basically an array of segmented lead fluoride that looks like glass. When the decay electrons come in, they make a flash of light, and we read them out with silicon photomultipliers. We digitize the pulse here. So you can see sort of an example pulse where we can then extract from the amplitude and width the energy of the deposition, as well as the time of the pulse. And what's really interesting here is that the information about the muon spin is encoded in this signal. So if you look at the animation on the right-hand side, what you can see is that the number of electrons with a given energy will fluctuate as a function of time, depending on the relative alignment of the spin and the momentum vector. And by applying a software threshold, we are able to just look at electrons which have high energy, and we're able to plot them as a function of time. So this is a log plot, and what you can see here is actually this difference frequency, this omega A anomalous spin precession frequency as a function of time. Now, there are many curves on here. This is really just wrapped around. Normally, this plot would just extend all the way to the right-hand side. We've plotted it in this manner for ease of viewing, and you can really see this curve build up on the left-hand side, and that's how we measure the muon spin precession frequency. Okay, we need to understand other properties of the muons, so we also have a system of trackers. You can see that these are gaseous straw trackers on the right-hand side here. This cartoon on the top shows that we have 8 modules that sit in front of the calorimeter, and when the decay electron comes through them, we see hits in those trackers, and we can actually make a track from that. We can use this track information to look back into the storage region and understand where the muons lived as a function of space and where they decayed from. And you can see in this plot that the distribution is a bit offset, and that comes from the fact that our kick was not strong enough, and we didn't move the muon beam directly to the orbit that we actually wanted it on for this first run. So that's an important feature. So we also can measure these sort of beam dynamic properties that I alluded to, where the beam is swimming up and down and has breathing modes, using the inferred information from this tracker system. Okay, the fourth and last main step of the experiment is to map and track the magnetic field. And for this, we use nuclear magnetic resonance. Basically, what we do is we have a probe which has a sample inside of it that contains protons, and we tip the spins of those probes and let the proton spin precess in the same magnetic field that the muons have. And so therefore, we determine the field in terms of the proton precession frequency, and we call this omega p. Now, we use NMR in several different ways. The first is a trolley. There are 17 probes that actually go into the same physical space that the muons live in, and they map the field all the way around this ring every 3 days. Because we can't have this trolley in the ring while the muons are there, we have to then monitor with probes that are just adjacent to this region. They live just above and just below this vacuum region, and we monitor this continuously the entire time the muons are there. And finally, since these probes consist of real materials that have their own sort of magnetic perturbations and effects, we also have to tie this to an absolute standard. And so we have a series of probes. This is a cylindrical probe with a water sample. This is a spherical probe with a water sample. And this is a helium-3 probe. And what this allows us to do is absolute magnetometry, so that we can actually get the value of the magnetic field with these probes, and then we can transfer the calibration to these sort of less absolute probes that measure very, very regularly. Because we use NMR, we can then rewrite the anomalous magnetic moment in terms of 2 observables, namely the muon spin precession frequency and the proton spin precession frequency to understand the field. In addition to a series of physical constants that are all determined externally, and they're determined quite well with an uncertainty of about 25 parts per billion. And so there's a whole chain of things that have been measured that are known very, very well. In terms of the things that we have to measure, our ultimate goal is to get the uncertainty down to 140 part per billion with equal parts statistics and systematics. And just to frame that for you for a second, if you think about the population of Poland, and you want to ask the question, how many people are living in Poland right now at 4:50 p.m. On this date, you would have to get that answer right to a precision of 5 people in order to be doing 140 part per billion. So it's really an extraordinarily precise measurement that requires thinking about a lot of subtle effects. Of course, the observables that we want to have are not necessarily the exact things we measure. And so I'm not going to go through all the details of this, but I just really want to give you a flavor. Things related to the muon precession are in the numerator. There's, of course, the frequency that you measure from that wiggle plot, as well as corrections that come from beam dynamics effects. That's in the numerator. And then the denominator relies on measuring the magnetic field. We have to measure where the muons live. That's what this term is. We have to do that absolute calibration, which is this term. And then we have some transient fields, and I'll talk a little bit about that modify our measurement. Okay, so let me start with the numerator and just give you a sense of how we do this. So we take that wiggle plot, and if you zoom in, you can see the data in black. This is just a beautiful oscillation here, and we can fit it with a 5-parameter fit, which is shown in red. Those 5 parameters really describe the decaying amplitude due to the muons that are actually decaying, as well as an oscillation that comes from this muon spin precession frequency. And if we do this fit and subtract the fit from the data to look at the residuals, we can perform a fast Fourier transform on what's left, and we get this curve on the right-hand side. And what you can see here is that there are a variety of frequencies that still live in this data that are not described by this fit. This is expected. This is a real machine that has beam dynamics effects, such as these transverse oscillations, as well as loss mechanisms where muons don't get stored exactly in the area we care about. And this can happen in a time-dependent manner. So to get the muon precession frequency right, what we really have to do is this 22-parameter fit, which is extremely well motivated and includes this omega A term. If we look at the FFT of the residuals to this, we see the plot on the right. Things look very, very clean. And this tells us that we understand all of the different elements of our fit, and we understand what the muons are doing, and we know how fast they're precessing in that field. Now, I told you earlier that we use electric quads to contain the muons vertically and provide this restoring force. And this leads to an interesting effect, because you know that an electric field will transform into a motional magnetic field. And fortunately, the contribution comes with this coefficient. And if you choose the appropriate gamma, the relativistic gamma, for how fast these muons are going, you can actually set this term equal to 0, which means you reduce the contribution to the spin precession frequency from the fact that you have an electric field. And so this is sort of one of the awesome things about this experiment, is that it can happen at all by having a magnet with this size and strength. Of course, the muon beam itself has a spread in momenta, so that means there's a spread in the relativistic gamma of those particles. And there are actual modes that take the muons off the ideal orbit, which means that sometimes muons do see electric fields. And so it's very important that we understand where the muons are. Here are 4 curves from some of our data sets that show where the muons lived in the horizontal plane. Ideally, they would live at this center point, but due to the underkicking, they were actually about 6 millimeters too high. And this leads to a rather large correction of about 490 part per billion for this run 1 data set. However, due to our knowledge of where the muons live in the volume, the uncertainty is constrained to about 50 parts per billion. By making the kicker stronger for subsequent runs, we were able to suppress this effect. And so going forward, so this is the error table from the experiment. I'll show this a few times. I just want to point out that this measurement of the muon precession frequency is statistically dominated for this data set at 435 part per billion. All of the rest of the effects associated with the measurement of the muon precession amount to 56 part per billion. We do have some large corrections from the beam dynamics effects, but the uncertainties are pretty well understood and are going to improve in subsequent runs. And I encourage you to go ahead and look at some of the papers that detail these effects that we published a few weeks ago. Okay, I'm going to briefly turn back to the denominator and tell you about the magnetic field. So the first step was to create a highly uniform field. This is important because if you want to know where the field is in a specific point in space, it's a lot easier if you're not sitting on a large gradient. The next step is that we have these 17 trolley probes, and we move it around in the field, and we make a map at 8,000 locations along the azimuth, and we determine the strength of the field versus space. So here you can see a series of magnetic field maps in the storage volume evolving as a function of the angle around the ring. We can then produce an azimuthally averaged field here. And what we do all throughout the analysis is, with our knowledge of the field and our knowledge of the muons in the ring, we basically weight the field map by the muon distribution. Ultimately, the fact that there are gradients means that the magnetic field shifts by about 100 parts per billion with respect to sort of the average field in this region. And the uncertainties are on the 20 part per billion level. There's also another important systematic that comes from the fact that the trolley only measures when the beam is off, and the fixed probes that live above and below measure while the beam is on. Because the magnet is not perfectly stable. The temperature drifts a little bit, and this leads to drifts in higher order field gradients, some of which those fixed probes cannot track. And so if we take a trolley run at one point in time and we look at the relative field, and we look at the field, and we look at a trolley at another point in time, okay, those are actual maps. In between, the orange curve shows the fixed probes and what they do. And what you can see here is that by the time we got to the second trolley measurement, the calibration between those two did not agree precisely. And what we can do over all of our data is we can quantify how much on average this tends to get off and characterize this as a systematic uncertainty. Because this process sort of happens randomly and scatters around, this ends up being something that reduces the more measurements you take. So we end up with an uncertainty in the 20 to 40 part per billion range. The plot in the upper right just summarizes in orange all of the different points where the trolley measured, and in blue are tracking in between. I just want to highlight this region here because these two trolley runs had a very similar value, and you can see there was an excursion in the field in between. And so it's really important that we monitor the field in between to know that we're getting the right value. All right, the last effect I'll tell you about are transient fields. So we do pulse these quads synchronously with the muon injection, and we observe a motion of the quad plates that is associated with these pulses. Okay, so the side plates of the quadrupoles are oscillating radially at a very small level. And this oscillating conductor perturbs the magnetic field in the region where the muons live. And we can actually sense this a little bit with our fixed probes that live outside the vacuum. The reason this is so important is that it affects the fields that the muons experience, but it is not mapped directly by the trolley. We have to turn off these quads during the time that we during the time that we measure with the trolley due to some of its sensitive electronics. So a dedicated measurement was performed to insert probes, special probes that could live inside this electric field region while we actually pulse them, so we can map out that field. And you'll remember I say we pulse the experiment 16 times per second. This is what happens to the magnetic field when we make these pulses. So you can see sort of hundreds of part per billion variations here. If we zoom into one of these gray regions, this is actually the region we care about, because this is when the muons are in the ring and when we perform our muon measurement. And so we have to characterize this really well. So if we map this effect all the way along the quad and account for the quad pulse variations, this leads to a 17 part per billion correction with a very conservative uncertainty of 80 part per billion for this run. We've performed better maps, and we will quantify the long-term stability to improve this. So I'll just summarize the magnetic field and get to the final results. So we have, again, a 56 part per billion uncertainty from the field mapping, tracking, and weighting, as well as the absolute calibration. This transient field was sort of dominant in our run one analysis with the 99 part per billion, and we have this PRA paper detailing everything. All right, one of the last steps is that we have this, this clock. It's really important for us to try to prevent bias in our experiment and not steer the answer one way or the other. We should just measure what we can measure. And the way we do this is by detuning the clock a little bit and not revealing the frequency to any of the experimenters. So we have to look at all the data and understand that things are consistent internally. And at that point, the collaboration basically unblinds and we understand what the metric for the wiggle plot is. And we learn the clock frequency and simultaneously a mu. So let's show you just what that looked like. So Brookhaven made this measurement and motivated our experiment. And when we unblinded the clock, we found a measurement that was very consistent with Brookhaven's measurement with the error bars. You can see here that both of these measurements were statistically limited. The systematic component is actually quite small when added in quadrature there. And because of this, we are able to average these two and produce a new world average for the experimental measurement that has a total uncertainty of 350 parts per billion. And this compares to the theoretical prediction that was published last year in the standard model. It has increased the discrepancy between the experiment and that calculation to 4.2 standard deviations. So this is what we say has strengthened the evidence of new physics, and is a very exciting result for us, both because the experiments agree and because that discrepancy exists. All right, so in summary, we agree very well. We have only analyzed 6% of the planned data. This corresponds to our run one data set. It's a statistically limited measurement with systematics that are starting to approach our target goal of 100 part per billion. As of today, we've collected more than 50% of our planned data, and we aim to analyze run 2 and 3 for next summer. Meanwhile, we really need to turn to our colleagues in theory to step in and answer the question, what could it all mean? And I just want to highlight that 2 weeks in, we already have had 77 different theory groups trying to answer that question. So at this point, I just want to thank you for your attention and hand things back for the theory part.
Thank you, Brendan, very much for this very nice overview and giving some flavor of the experiment and the difficulties. So I would propose now to switch to the theory talk, and then we can have discussion to those. So the theory talk will be given by Dominik Stoeckinger. He graduated from, oh, by the way, I don't know, but you did your PhD in Karlsruhe with Wolfgang Hollig on renormalization methods in supersymmetric gauge theories, but his first scientific paper was actually on magnetic dipole moments, weak magnetic dipole moments. And so Dominik did his PhD in 2001, and then in 2002 he moved to DAISY for postdoc for 4 years, and then going through Durham, Edinburgh, and Glasgow, he ended up in Technical University in Dresden, where he is now a chair for phenomenology of elementary particle physics. So he is really an expert on doing theoretical calculations, not only the standard model, but also beyond the standard model. So Dominik, the floor is yours, please.
Thank you very much, Jan, for this kind invitation. It's really a pleasure and an honor to give this talk here after Brendan explained so nicely the experiment. Just a double check, can you hear me and see the screen well? And is my video switched on correctly?
Yes, yes.
Okay, thank you very much. So then I will speak both on standard model theory, which gives rise to this prediction that we just saw, and on potential interpretations in physics beyond the standard model. Let us begin again with the standard model of particle physics. The standard model of particle physics is one of the best theories in physics, and actually it's not a new theory, it is almost 50 years old, and in those 50 years it has been established extremely well in a multitude of many different experiments. So it describes all known interactions between particles except for gravity, and it is based on very fundamental rigorous principles. It is a relativistic quantum field theory, which is renormalizable, which means that it has a finite number of parameters and is very predictive. It uses the principle of gauge invariance, which is very restrictive and gives rise to specific relationships between all the different interactions that we have. And it uses the concept of electroweak symmetry breaking spontaneously, which gives rise to the Higgs field and the Higgs potential and the Higgs boson, of course. And again, this also restricts very strongly the possible interactions. And all these different constraints from relativity, gauge invariance, spontaneous symmetry breaking, they are all confirmed in many, many different experiments. And G-2 or A mu is a single quantity which is unique because it's really sensitive to all particles and all forces that we have here. And the sensitivity comes via quantum fluctuations. So let me explain a little bit what we mean by those quantum fluctuations. And to explain it, we can really go back to the essence of quantum mechanics according to Feynman. This is the double slit experiment. So the double slit experiment tells us that if a process can happen in two different ways, like the particle can go through the first slit or the second slit, each possibility or each path gets a probability amplitude, which is complex, and the probability amplitudes all contribute and they interfere constructively or destructively. And what we see in the end as probabilities is an interference pattern. So here in the double slit experiment, of course, this is a paradigm experiment and both slits contribute equally. Let's imagine we drill a third slit in green here, which may be very, very far away. Then there is a third kind of path going through the green slit, which contributes just a little bit, but it also contributes and will change the interference pattern. So in general, all possible paths contribute and the probability amplitudes interfere. Now for G-2, our paths are the Feynman diagrams. We need a coupling of the muon to the magnetic field, and this coupling can proceed directly or via the exchange of virtual particles described by Feynman diagrams. And so the simplest path or the simplest slit in our double slit experiment, if you want, is this three-level Feynman diagram where the muon directly interacts with the magnetic field with nothing in between. And this Feynman diagram is the same as the famous Dirac equation. You could call it a direct interaction of the pure muon in a point-like fashion with a magnetic field. And this, if you calculate it, gives directly G exactly equal to 2. Now there are other Feynman diagrams or other paths in our double slit experiment, which is, for example, this famous Schwinger diagram, which was calculated by Schwinger in 1948. Contributing to his Nobel Prize for quantum electrodynamics. And here the muon first emits a virtual photon, then it interacts with the magnetic field and reabsorbs the virtual photon again. So you could call this a quantum fluctuation where the particle number is changed for a short time, or you could say it's a non-point-like correction to the interaction with the magnetic field. And the calculation gives the famous alpha over 2 pi factor, which is 1 per mil, roughly speaking. And this is really the main effect, the most important contribution to G-2, but of course not the only one. So just technically, we can express all of this in terms of effective Lagrangians and effective Hamiltonians, which we can derive from the Feynman diagrams. And then you can look at the right bottom here and see how the effective Hamiltonian looks like, which contains this A mu quantity in relationship to the magnetic field and the spin of the muon. But going back to Feynman diagrams, I said all particles and all interactions contribute. And just to give you the other end of the spectrum, so here is maybe the most exotic Feynman diagram in the standard model you can think of. It involves the two heaviest known particles, the Higgs boson and the top quark. So even this contributes here. The muon would first emit a Higgs boson, which is of course extremely unlikely because the Higgs is so heavy. And then the Higgs even dissociates into a top quark, anti-top quark pair. And the top quark is really the heaviest particle that we have ever seen in an experiment. And then the top interacts with the magnetic field. So via this complicated affair, the muon can also interact with the magnetic field. And this gives a correction to G-2 of the order 1.5 times 10 to the minus 11. So it's an extremely small correction, but it again illustrates everything contributes. So everything contributes, and that means, of course, the full calculation of the prediction of G-2 in the standard model is an extremely complicated, but obviously a very important calculation. And in order to consolidate it as much as possible, a worldwide theory initiative has been formed some years ago. It has held several workshops and produced a very extensive white paper, with lots of authors, and this is kind of has the attitude of combining all the existing approaches in a conservative way to come up with a really stable and solid standard model prediction. And you see the final result here at the top. It has an uncertainty of around 4 times 10 to the minus 10, which is just about the same as the experimental uncertainty that we have right now. So this is one of the most precise predictions that we have in the full standard model. And you could write textbooks about all the quantum field theory methods that are used in this, because essentially all tricks and methods that have been conceived in quantum field theory are applied in order to get this prediction. So let me just give you some highlights. We can start with the QED contributions at the top. They are most important, and I showed you the Schwinger diagram, which is 1 per mil, but we can calculate many more complicated Feynman diagrams, and the current status is that 4-loop and even 5-loop diagrams are taken into account. There are many of them, and each one is extremely complicated, and so this gives rise to high precision perturbative methods involving interesting mathematics of Feynman integrals, giving rise to nice analytical formulas and also code generating computer programs for the numerical evaluation. And by the way, if one applies this to the G-2 of the electron, then this gives rise to the most precise test of quantum electrodynamics. Then there are also effects from the weak interaction, like the one with the Higgs and top, but not only this. And so those are calculated at the 2-loop level, also using perturbative Feynman diagrams. And it was the first ever full electroweak 2-loop calculation, so also some kind of a record. But not only explicit diagrams are used, one can also refine the calculation using interesting renormalization group and effective field theory methods to get higher precision. Then let us turn to those two so-called hadronic contributions at the bottom left. So there are one where the photon dissociates into a hadronic blob, like pions, kaons, and so on in the blob. Or we can have a 4-point function with 4 photons connected by hadronic blobs. And so first, for these first kind vacuum polarization contributions, they cannot be evaluated directly using Feynman diagrams because the hadrons interact strongly and perturbation theory cannot be applied. So something else comes to the rescue, namely from fundamental principles of relativistic quantum field theory. There are unitarity and causality relations which give rise to so-called dispersion relations. And those are exact relationships which allow us to relate those desired G-2 diagrams with hadrons to experimental data, and those experimental data are taken in experiments E plus E minus scattering into hadrons at very low energies. So these are not very famous experiments, but they are very important, and there exist many of them which cross-check each other, and they give rise to the number that I quote here on the slide. There is also another method coming into play recently, namely from Lattice Qcd, which is a numerical simulation of the quantum field theory, also on a non-perturbative level. There is impressive progress from this, but currently this is not yet at a level of precision required to be included in this white paper prediction, but it might well be in the not so far future. Then finally, these hadronic light-by-light contributions are similarly non-perturbative. They are a very difficult quantum field theory problem with many different scales. And here, the same 2 kinds of methods can be applied, using dispersion relations or using Lattice Qcd results. But also people have used so-called low-energy hadronic models, which are model field theories describing the essential physics of hadrons. And so all these 3 ways currently agree very well with each other, which leads to cross-checks. And the uncertainty estimation here is rather stable because of this cross-checks between the different methods. So this gives rise to the final number, which Brendan has already showed, and the discrepancy is 4.2 sigma. And so let us now ask the question, What can it mean if we take seriously the idea that this could be due to physics beyond the standard model? Of course, we have the threshold of 5 sigma, which is not yet surpassed, but it might well be in the future. And anyway, we can ask the question, how could this be accommodated by potential physics beyond the standard model? Now, if we turn to this question, let's zoom out a little bit and say the number is that we need to explain is 25 plus minus 6 times 10 to the minus 10. At first sight, this looks like a very, very small effect, significant but small. But actually, I want to stress that this is a large effect, and it's not easy to explain this. Why is it large? Because it is almost twice as large as the contributions from the weak interactions. So we know very well the weak interactions from W and Z bosons and the Higgs and so on. They amount only to 15, but the discrepancy is 25 in these units. And so therefore, you can ask, how could it be possible that new physics contributes twice as much as weak interactions here, but is essentially invisible in all other experiments, in particular at the LHC. So that is not obviously how it could be answered. And that is why all these questions here are very meaningful. So we should ask now, what are the models which can explain this, if anything? Some models will for sure not be able to explain it. And of course, this explains to you why this single number is so interesting, because it really singles out only a few models out of the spectrum of all potential theories for beyond the standard model. And that makes us happy, of course. So this is a very active area, as Brendan already mentioned. And in this talk here, in the next 10 minutes or so, I will give quite broad general remarks on the situation. And I will give a few selected examples from a rather extensive survey here. So let's look once again at this picture for the standard model and the known particles and forces. It, of course, is very good, but leaves open relevant questions. And first and foremost, there are some observational facts. Like, we know that dark matter must exist in the universe, but it cannot be described by the standard model. Therefore, this requires going beyond the standard model. Dark matter is one of the really important open questions. But there are also some conceptual questions which are interesting. Like, looking at the table here, you see 3 generations of quarks and 3 generations of leptons. Who has ordered these 3 generations of particles? What is their origin? We don't know this. Why are there quarks and leptons in the first place, and not only one of them? On a technical level, let me say that those structures here are expressed by so-called Yukawa matrices in the theory, and so we could ask technically, what is the origin of those Yukawa matrices and Yukawa couplings? On the other hand, there is just a single Higgs. Why not 3 generations of Higgses? Why not many Higgses? We don't know. We only know one Higgs so far, but maybe there are several. And at any rate, we would like to understand where the Higgs mechanism and this Mexican head structure of the Higgs potential and the Higgs mass, where does it all come from? We would like to know this, and in order to get answers, we need somehow to get beyond the standard model. And so these yellow questions that I highlighted here are the particular questions that can be related to G-2, as I want to illustrate in the following. So let me first illustrate the connection to dark matter here in blue. So dark matter is, of course, a kind of particles which is electrically neutral, and it is only weakly interacting, which by definition means it is hard to observe in detectors, right? But it could very well be that dark matter particles couple to the muon, and then we would get via these loop Feynman diagrams a contribution to G-2, while dark matter particles cannot be observed elsewhere. So indeed, this is a very natural idea, and as you see here, more than 15 papers in the last weeks already pursued this avenue to explain the G-2 result. The other thing is that G-2 provides a window to the muon mass generation mechanism, and that is even more interesting and more important and kind of deeper. So let me explain it a little bit more in detail. On a technical level, what I mean is that the quantum field theory operators for the 2 quantities, mass and G-2, are very similar. Both involve what we call a chirality flip and break gauge invariance. On a non-technical level, we can understand this connection to the muon mass as follows. So Brendan has showed this nice picture here, which makes clear that G-2 is really a relative rotation of the muon spin compared to the momentum of the muon. So such a continuous spin rotation is only possible if a particle has a rest frame and a non-zero rest mass. So in the rest frame of the particle, the spin just rotates continuously. And compare this to the photon, for example. The photon is massless and it always moves at the speed of light. And the photon helicity and spin can only point either forward or backward. The photon spin can never have an angle compared to the momentum. So in order for G-2 to make sense at all, we need a rest mass which is non-zero. And this is the connection between G-2 and the muon mass. And in the standard model, of course, the muon mass arises in this very complicated way, not directly, but by coupling the muon to the Higgs field. So the coupling of the muon is given by this Yukawa matrix element. And the Higgs field is coming from the Mexican head structure of the Higgs potential, which has a non-trivial minimum. Okay, so this is the mass mechanism for the muon. Now, we would like to make progress in understanding where the Higgs potential comes from, where the Yukawa couplings come from. Now imagine any new physics model or a BSM scenario which changes the Yukawa structure or the Higgs potential structure. Then very easily and naturally you get very strong modifications also of G-2 of the muon. So in that sense, measuring G-2 precisely gives a sensitive probe into new physics modifications of the muon mass generation mechanism. And so that is very interesting. And at the top, you see a small list of papers. So the vast majority, probably 30, 40 papers describe G-2 in this sort of way. Many different kinds of models, but they all share this feature of changing the muon mass mechanism and giving rise to what we call chirality flip enhancements. So let me give you one example how this can work in detail. Let us imagine you would like to have a BSM idea with these properties. So you would like it to be beautiful and fundamentally rooted in terms of new symmetries of basic quantum field theory. You would like it to improve the situation of the Higgs. Maybe it should predict the Higgs potential, should predict the Higgs boson mass instead of having it as a free parameter. It should solve the dark matter problem by explaining dark matter with a suitable particle candidate. And it should explain G-2 in terms of such a chirality flip enhancement. And of course, it shouldn't be excluded by the LHC. So what could that be? And of course, this is the minimal supersymmetric standard model, which is very well known in Warsaw, where many experts work on this model. And it really is a model which ticks all these boxes that I mentioned before. It is well known that it can explain G-2, and it was constrained significantly by the LHC. But let me discuss its situation. So supersymmetry, first of all, predicts that each known particle has a supersymmetric partner of different spin, and it improves significantly the Higgs sector. And in detail, we have two relevant parameters now for us. One is called tan beta. It is the ratio of two vacuum expectation values. And the other one is the so-called Higgsino mass mu. And the Higgsino is the supersymmetric partner of the Higgs boson. So having this, please look at the top where you see a sketch for a G-2 Feynman diagram and the resulting value of G-2. So G-2 is now obtained from this diagram where the muon emits first a Higgsino, the superpartner of the Higgs. Then this is converted into a gaugino, the superpartner of the gauge bosons, and at the bottom we have a neutrino, the superpartner of the neutrino. So this Feynman diagram involves this extended Higgs sector and this supersymmetrized Higgs sector. And the numbers work out like this, so we can explain the current 25 times 10 to the minus 10 very nicely if, for example, tan beta is 50, mu and all the other SUSY masses are of the order 500 GeV. So these are very typical and quite natural reasonable parameters for this model. So it can explain the currently observed deviation very nicely. Let us look now at this plot that I showed here. It is one example plot of a supersymmetric parameter slice. What we plot here is the dark matter mass in the y-axis and this Higgsino mass at the x-axis. And in green, you see the region which explains the current G-2 value. So the G-2 value is explained in a rather broad region, and the green region would become even wider if we would change the value of tan beta, which is fixed here. But if we change it, the region goes higher and lower. So in this plot, dark matter is also explained, and dark matter is explained by something we call Stau or Slepton co-annihilation. And this mechanism means that several SUSY masses are very similar to each other. So we chose here a mass splitting of around 50 GeV. And once we choose such a small mass splitting to explain dark matter, then automatically the LHC limits are evaded. And that explains why here in this entire plot you do not see any limits from the LHC. In fact, we checked, and the entire parameter range you see here is completely allowed by the LHC, by the Large Hadron Collider. Even though many people hear from time to time that the LHC claims a lot of supersymmetry parameter space is excluded, or supersymmetry is almost dead, and so on. So you see here a counterexample. On the other hand, to make LHC physicists happy, it is absolutely true that the LHC excludes a part of the SUSY parameter space. And here is an example where you see this. So the entire blue region is excluded by LHC data. But you see, now we plot here on the y-axis a value M2, which is a so-called Higgsino mass. And in the previous case, we chose that mass to be around 1 TeV, which is above the LHC limits. And as you saw before, this mass of 1 TeV is perfectly compatible with explaining G-2 and dark matter. But lower masses are indeed excluded by the LHC. But you see also something else, namely at the lower border of the plot, there is again a viable region which is not excluded by the LHC. And this is again because here the mass splittings between different particles become very small. And in fact, here we can explain dark matter by chargino-neutralino co-annihilation, which is another mechanism which is also attractive. So again, we have different ways to accommodate all observables, but it is in fact true that the LHC excludes a large part of the parameter space, but very relevant and meaningful parameter space remains viable. Let me give you just one second example very briefly, since it's also well known in Warsaw. I'm talking about the 2 Higgs doublet model, which is a non-supersymmetric extension of the standard model, where we just implement the idea of having an extended Higgs sector and also a richer sector involving those Yukawa matrices. So many Warsaw experts have pioneered work on the so-called type 2 version of this model in particular, which is now excluded as an explanation of G-2. So you see also the power of exclusions from G-2, but here I focus on the aligned 2 Higgs doublet model, which is more general. And in this aligned model, G-2 can be accommodated, and the relevant Feynman diagram is shown here on the left. The muon emits again a Higgs boson, but it's now a new non-standard model Higgs, and the Higgs couples to a tau loop or a top quark loop. And
5 minutes.
Okay, yeah, thanks. That is fine. So it's my next to last slide. And right, so in order to maximize the contributions to G-2, we can invoke large couplings from the Higgs to the top quark, but then there are indeed relevant constraints from the Large Hadron Collider, where such new Higgs bosons can be produced via gluon fusion and also with such a top quark loop. So if the new Higgs couples strongly to the top quark, then it would be produced by the LHC and it would decay into tau leptons in a visible manner. And so at some point this is excluded. The LHC has not seen this process. And that means we have an upper limit on the possible couplings. And because of this upper limit on the couplings, you see in the plot on the right that we get an upper limit on the possible values for G minus 2. And the upper limit is just a little bit higher than the currently observed deviation, which means that if the next runs of the Fermilab measurement give rise to a slightly larger deviation, or the LHC limits become just a little bit stronger, this model might also be excluded in the future as a possible explanation of G minus 2. Or of course, we might find this process at the LHC. So let me just flash this slide to make clear that I showed you only 2 examples, but there are many models which can explain the current G minus 2 deviation. I will not go into any detail, but I want just to let you know that there are many possible explanations. And in red, you see that many interesting models are already excluded as possible explanations, which shows the power of G minus 2. And in the green cases, you will always have interesting constraints from other measurements like LHC or dark matter measurements and so on. So let me, however, summarize. The standard model prediction for G minus 2 is really an incredibly interesting quantum field theory calculation. All known particles are relevant, and if you want, all quantum field theory tricks as well. The theory initiative is an ongoing effort which will further improve the value in the future. And currently we have this agreed and conservative value, which gives rise to this 4.2 sigma deviation. If we want to explain the deviation in beyond the standard model physics, we need a large effect, larger than the weak contributions. And because of this, we get these interesting connections to deep questions like dark matter, origin of flavor, or origin of the Higgs potential. There are many viable models which can explain it, but in all cases, we get interesting and relevant constraints from the LHC and also from dark matter experiments and others. As an outlook, let me again reiterate that Fermilab has already taken data from run 2 and 3, and there will be further data from the forthcoming runs. So there will be very interesting and promising progress in the standard model case. In particular, those mentioned lattice calculations will be further scrutinized and will improve. There will be also more data available for these dispersion relations. And in the case of beyond the standard model, I should say that I gave you only 2 examples, but there are many examples and you can go through all of them, and you see that many new experiments are now motivated to further disentangle between all the different potential explanations of G minus 2. So finally, let me say that 20 years after the Brookhaven experiment discovered this deviation for the first time, and after all these improvements in experiment and theory, now the deviation has been confirmed, and we are looking forward to a very promising and exciting future. So thank you very much for your attention.
Thank you very much, Dominik, for this nice explanation and overview. And again, thanks goes to Brendan. So now the talks are open for discussion, for questions. So please raise your hand if you want to. Mikołaj. Okay, so you have to unmute. Mikołaj Misiak, can you unmute yourself? Mikołaj.
Yes, I can, but it took a second. I'm sorry.
Yes, we can hear you.
Yes. So I have a question to your slide when you were saying this effective interaction of dimension 5 with F mu nu. Could we go back?
Okay, it's a question to me. Okay, yes. Just a second.
Beginning of the.
It's quite slow. Here. Yes.
Yeah.
Yes. So in principle, in the Lagrangian, we can have higher order terms suppressed by higher powers of m mu squared and with more powers of f mu nu. These terms definitely give small contributions because the magnetic field when expressed in electronvolts is much smaller than the muon mass squared. But of course, the precision of the experiment is also very large. So do you have the orders of magnitude on the top of your head to compare that the second order effects in the magnetic field are unimportant?
Yes, this is an excellent question. And of course, it touches this overall question. Are there some maybe unaccounted for effects, or do we calculate the correct quantity in quantum field theory when comparing to this high precision experiment? And so indeed, there would be these higher order terms in the magnetic field, nonlinear effects. And I don't know the numbers out of the top of my head, but what I know is that it has been analyzed in particular for the case of the electron G-2, where Kinoshita has analyzed this in detail, and the second order term drops out because of symmetry reasons, and the third order term is already down by, okay, I don't recall it by heart, but it was something like maybe 20 orders of magnitude, something like this. Definitely many orders of magnitude more than to give you any reason to worry. So you don't need to take into account those higher order terms.
Okay, thank you very much.
Okay, so are there any other questions?
There is a question.
There is a question from Jacek Dobaczewski. Can you switch your microphone, or maybe I can read what you have? So Jacek, probably he cannot. So Dominik, what is your take on the calculation of G-2 that does agree with the measurement of Borsiani, which was published in Nature on 7th of April, 2021? Is it justified not to even mention this work?
Well, I'm happy to mention it now, and it's perfectly justified to mention it now in the question time, but I think it was justified not to mention it explicitly in the previous talk, given that we had only 2 times 25 minutes, and it's not yet included in the official standard model evaluation, but absolutely it's fine to discuss it now. So maybe I can give 2 kinds of comments on this result. So the first comment is on the promise of lattice calculations in general. So of course it's extremely good and promising that the lattice calculations are catching up and now are becoming competitive with the traditional data-based E plus E minus data results from dispersion relations on the hadronic vacuum polarization. Maybe I can also show the slide so that everybody can see what we are talking about. So the progress by lattice is very promising, and at the moment there is this first precise lattice result by one collaboration which came in too late, and it was not really cross-checked by other lattice groups to be incorporated in this theory initiative white paper. But now many lattice groups are scrutinizing this result, and there are many detailed comparisons, for example, by splitting up the lattice result into different sub-results for individual energy ranges and so on. And so what needs to happen is that the lattice community result which really agrees between different lattice discretizations and so on. And this has not yet happened completely, but progress is of course ongoing, and that is definitely promising. Then let me say, and maybe I can show a slide which I took over from Thomas Teubner, who is also a member of the theory initiative and in the steering committee of it. So he has this compilation of many numbers. So here is his compilation, and you see at the second line from the top is the new result that you were mentioning from the BMW lattice collaboration. And it doesn't get rid of the discrepancy to the Fermilab measurement. It is exactly in the middle. It is in the middle between the standard model prediction from the theory initiative, which is the gray band at the bottom, and between the experiment. So using this new lattice result would not eliminate the discrepancy, but it would of course make it smaller if we take it at face value. But as I said before, the lattice community overall needs to converge. And you see here in blue this cloud of many different lattice points. Of course, this will all improve in the future. But let me please give also a second answer, which is sometimes a little bit overlooked, or at least not stressed enough in my opinion. So even if there is a convergence of the lattice results to some value, we don't know to which one, but let's imagine this, then those gray results here at the bottom from the dispersion relations, they still stand. They are based on rigorous non-perturbative quantum field theory coming from causality and unitarity and experimental data taken by many, many different experiments using different experimental techniques. So they are not wrong. At least nobody has come up with a reason why those gray results could be wrong, and therefore they need to be taken into account in the future as well, independently of what the lattice results come up with. So the discrepancy between the gray results, which are true standard model predictions, and the experiment will remain unless somebody comes up with a bug report. But this is not foreseen. So these results are, of course, obtained by many different groups using different details, and this is cross-checked and done already for decades. So these results should not be ignored because of the emergence of very promising lattice results.
Thank you. So other questions?
May I ask Brandon a question?
Yeah. Okay, go ahead.
Namely, because I cannot raise a hand as I'm the host. Brandon, for the coming runs, do you see any immediate necessity of experimental improvement in any aspect of your hardware, or I don't know, data treatment maybe shows something which absolutely has to be improved? Do you already have things like this, or will you proceed according to the same paradigm and the same equipment without any changing, just collecting more statistics?
Yes, so I will just reshare very quickly the, oh shoot. Just a second.
Meanwhile, when you share your slides, I will add, we are not just the particle community here. So to 90% of us here, maybe certain abbreviations and ideas are not so clear.
Oh.
But I think the experimental setup was fairly physically, I mean, independent on speciality.
Yeah, so let me just go into this plot a little bit more. This is our data sets. So right now, today, we are in the middle of run 4. So your question goes to whether we had to do changes to the experimental setup or whether we had to do changes to the analysis.
Any improvement
Yeah.
of the hardware or data treatment?
Yeah. So in the so we showed you the analysis from this, and in this long period between run 1 and run 2, we did make a variety of improvements. Let's just start with the hardware. Because we underkicked, we had to go through a rigorous process to improve the robustness of our kicker to be able to operate at higher voltages to move the beam onto the appropriate orbit, the muon beam in our storage ring. So this will have the effect of reducing some of the beam dynamic systematics and centering the beam better within the magnetic field. We also had large temperature variations in the Hall. Sometimes you see a picture of our ring with the blue steel visible, and other times you see this sort of white cover on the top. We put a thermal blanket on the magnet to reduce fluctuations in the temperature from the equilibrium bath that it lives in, or the temperature bath that it lives in. And we invested in a system to control the temperature of the Hall much more precisely. So we now have a full range fluctuation during our measurement of less than 1 degree C. So this is really important for keeping the magnetic field stable. There was a failure also of some of the high voltage resistors that pulse the electric quadrupoles. during run 1 that caused us to have to make a special analysis, and these were also addressed and monitored. So there were 3 sort of rather large things that will be improved, as well as the mapping of this quad transient that I spoke about at the very end. So I think that those improvements really are in place here for the run 2 and run 3 data sets. And for the most part, the improvements are hardware based. In terms of the analysis, there are a few things that people would like to do in a little bit more detail. As we push down in precision and the systematics start to play a larger role because the statistics will come down, we really want to make sure that we understand the systematics at an extraordinarily exquisite level. So there are a few techniques that people wanted to do. For example, in the magnetic fields, we did cross checks with 3D magnetic field fits, but ultimately the analysis did not require it for run 1. I think we'd like to advance the magnetic field analysis a little bit there. But for the most part, the analysis techniques for run 2 and 3 will be pretty much the same, with maybe modest improvements. And most of the improvement come from the increased statistics and the improved hardware configurations.
Mm-hmm. Okay, thank you.
Thank you.
And maybe the last
question from Jan Berezinski. Jan?
Yes. Some time ago, I heard about discrepancies with measurement of the proton radius as probed by muons and as probed by electrons. Now, what is the situation with respect to that discrepancy, and is it related to G-2 discrepancy?
So I don't know, Dominik, would you like me to talk on this, or?
Yeah, go ahead, please.
Yeah, so there was for quite some time this discrepancy. So there's 2 different axes, right? You can do scattering measurements and you can do spectroscopy measurements. And the muonic and hydrogenic spectroscopy were in big disagreement with each other for the extraction of the proton radius. And there was a big mystery and question there. I think there still is tension, but some of the later hydrogenic spectroscopy measurements seem to be more in line with the muonic system. And so it is really hard to interpret. The original questions that tried to tie them potentially to G-2, asked to the muon G-2, asked, is something special about muons that is causing muons to see the protons differently? And that, of course, motivated doing muon scattering experiments, which are proposed to run to fill out this 4th quadrant of the scattering spectroscopy muon electron space. So personally, I am not really sure what the best consensus is, except to say that there are some discrepancies there, but they are not fully between muons and electrons anymore. Dominik, do you want to add any more on the interpretation, or?
Yeah, well, I cannot add something particularly deep, except for saying that it always was not easy to explain with some unified beyond the standard model framework all these different observations. So it seems that G-2 is, if it is a real discrepancy between the G-2 experiment and the standard model prediction, should be caused by something else than the proton charge radius puzzle. And in the proton charge radius case, the discrepancies between these various measurements seem to go down as soon as the measurements are improving. And when this proton charge radius puzzle was discovered for the first time, some of the measurements that went into it were rather old. And so once they became improved, the discrepancies became smaller, but they still persist to some extent. And so therefore, of course, there is still something that needs to be improved in that respect as well.
Thank you.
I have a question to Dominik. I mean, there are these B meson anomalies which are not understood. So can you relate, or in your survey of various models, can you at the same time accommodate G-2 and some of these B anomalies?
This is a very interesting thing to think about. Of course, it's an obvious question, and it turns out to be not so easy. So, of course, the kind of observable is quite different. Muons are involved in both cases, but the way they need to interact is rather different. In particular, given the fact that in the case of B physics observables, many B physics observables agree very well with the standard model prediction, and only some specific ones show these slight deviations. And so one needs specific kind of interactions to make it happen that only those observables show a signal and the other ones don't. And in contrast, for G-2, you get quite generically contributions from many ideas for physics beyond the standard model if you have these enhanced chirality flips and Yukawa sectors. So one way to explain the B-physics anomalies is in particular with leptoquarks, these particles which connect leptons and quarks at the same time. And you need quite specific properties of those leptoquarks. For example, spin 1 is preferred compared to spin 0, and particular patterns of flavor kind of couplings of the leptoquarks are also preferred. Now, some of those leptoquarks which can accommodate the B-physics anomalies can also accommodate G-2. It's a subset, and a particularly small subset, which means, of course, if all of those signals are true, then we have an extremely, let's say, strong hint to a small set of possible BSM scenarios, which is, of course, very nice. But I just want to say the opposite is not true. So if you explain G-2 with leptoquarks, then generically you cannot explain directly also the B-physics anomalies. So the difficulty to explain everything simultaneously is kind of illustrated in a nice way by a recent study which was done by a group involving Lorenzo Calippi. And they investigated systematically models with 1, 2, 3 new particles. And so they would say one new particle suffices to explain G-2, 3 new particles suffice to explain G-2 and dark matter simultaneously. And you need 4 new particles to explain dark matter, G-2, and B-physics simultaneously, if you restrict yourself to a certain framework and so on. But this just highlights that those are quite tricky to explain simultaneously. So it is extremely interesting to see what happens to those tensions, of course.
Okay, thank you. So any other urgent questions? So I don't see any new hands raised. So let me thank again our both speakers. Thank you very much for this very exciting and very interesting talks and nice overviews of experimental and as well theoretical problems in this respect. Okay, thank you very much.
Thank you very much too.
Thank you for having us.
Bye.